That was a great way to start. All right, so we've talked about from the quantum level up to building the gates, and then I've started talking about Verilog. Now that we have gates, we want to actually build something that's useful, like for example, adding. Computer needs to be able to add. And we'll talk about muxes and decoders, which is basically selection and
So our computer needs
the
to be a
opposite.
calculator. Yeah.
Right. Well, that's all it is, right? Well, it's not even a walking calculator. It's a stationary calculator.
It doesn't walk. We walk
The
in.
minute it walks, we have a problem.
Hey, there is that AI.
All right, so again, real quick,
She just got legs. She can do
inverter. We've already talked about that. We just talked about these slides. All right, NAND, NOR, XOR.
Yeah, we did.
Great. All right, a little math. Wait, have any of y'all have to go through Common Core?
Isn't that the new stuff?
Yeah. Okay, good. So the answer is no. All right, great.
We're not that yet.
What is Common Core though?
It's a different way of teaching math to little
Is it
kids.
like that?
No, not at all.
I was about to say because that's gross.
I don't like that.
No, you have to use number sentences, number bonds. It doesn't. My daughter comes home and I want to just strangle whoever came up with this thing because it's not helpful. Instead of learning, that instead of learning that that's what it is, you're like, okay, guys, let's create circles. I mean, you did the circles and you put them together, but let's say you're trying to do 8 plus 7. So say, okay, let's make the circles, group them into 5s. All right, what's left? I'm like, all right, guys, look, we're first graders. Just learn that 7 plus 8 is 15.
Wait, why are they grouping the circles into 5?
Thank you.
This reminds me of the morning.
This would make sense if they're middle schoolers, but not first graders. Anyways, end of rant. I'm glad you have not been taught Common Core, which means that we can actually do this like sensible human beings.
I mean, we could have done it that way anyway, regardless, and just said, haha, to the other person.
Yeah, 125. You can keep in mind that if the first digit is 5 times 10 to the 0, aka 1, and the next one is 2 times 10 to the first, 10, and then the last one's 1 times 10 to the second, which is 100. Okay. Binary numbers work the same way. Have y'all seen this before?
Nope.
No. Okay, great.
Yeah.
So this is what I'm teaching you. Binary numbers, the same thing, except instead of using a 10, you use a 2. And since it's binary, you can only have a 0 or a 1.
You see, when I learned binary, it was just kind of like, you just like drew the 2 to the power below it. And so I just knew that it was like times the last one by 2 to get the next one.
No. You sure you weren't in Common Core?
It was here.
I'm kidding.
No, that was in high school, but I was taking a programming class.
All right, so what is this one over here? 1 times 2 to the first, that's 2, plus
And then binary
4
and someone else good at it.
plus 16. So that would be
Oh, wait, sorry.
22 in decimal.
Yes.
2 plus 4 plus 16. Okay. Remember, our computer is going to operate over here on the binary because if you remember, our wires only have high and low. We don't have, high,
Until they have high, low,
medium, low, low,
disconnected.
low, low, or something, and then different variable voltage. People have tried to do that, just for the record. It did not turn out well. It was not a good thing. Yeah, maybe more like epic fail. They were able to do some of it, but it's just not.
Okay,
It wasn't.
epic fail.
It was not a good thing.
Okay.
So we're going to stick with binary. So if you want to do decimal addition, and y'all learned it like real human beings, you would, 5 plus 7 is 2, and then you do what? Carry the 1, right? Well, we're doing amazing.
Whoa.
6, and then 3. Okay, in binary addition, guess what?
Same thing.
It's the same thing.
Yeah.
1 plus 1 is actually 0, carry the 1. Put the 1 up there. 1 plus 1 plus 0 is again 1. Or 0, sorry, 0. You're right.
Yeah.
Carry the 1. 1 plus 0 is 1. And there we go. Ooh, look, that last.
They're uneven.
Why is that?
Why?
That's amazing. Just trying to keep you on your
So it's
toes.
kind of like NAND, right? 1
Uh,
1 would be 0, and then another 1 1
yeah,
would be 0.
but you got to
And
figure out how you're
1
gonna.
plus 1
How
is
you
0,
gonna.
so put in the
That's right.
1.
Except
And
And
you
two
got to figure out
equals
about the
4.
carry bit, right?
So you just
Yeah.
carry the 1 to the 4 section.
So yeah, you're on the right track.
Yay.
So how do we do a half adder? All right, what?
What?
Okay, hold on.
What is
Okay,
this?
hold on. Roll with me. Again, half adder, you have two 1-bit numbers, A and B.
We're not round.
What?
Said he can't roll very well. We're not round.
Oh, because we're halfway. Okay. So the sum is the number that you would actually put, aka down here. That would be the sum, and then the carry is the number up here.
Interesting.
So 0 plus 0, the sum is 0, the carry is 0. 0 plus 1, the sum is 1, carry is 0. 1 plus 0, the sum again 1, carry is 0. 1 plus 1, the sum is 0, but the carry bit is 1. How could we create a circuit that implements that truth table? Well, what does the sum look like? Which one? It's actually just one gate.
It looks like the, what is it, the OR?
Close.
Or the XOR?
It's the XOR, and then what's the carry?
And?
The AND. And can those two, do those two need to be in sequential or can they be in parallel?
Parallel?
Parallel. All right. So we got an XOR for the sum and an AND for the carry. All right. You know, we didn't do the transistors for these. We should have. All right. So Boolean expressions, outputs determined exclusively by input, no memory, so there's no state machine. We haven't talked about a state machine yet. We'll get there. But right now, we're only doing a circuit for now. So a half adder, hopefully you can see why that's useful. You can at least start building up something for an adder. It's called half because we haven't done the full thing yet. Decoder is given a select line, put out a bunch of different signals, and a mux is select one of the input lines from what's being passed. All right, it's going to make more sense when we look at these pictures. All right, this truth table, what's going on is you have 0 and 1, and that's basically selecting which line you're activating out there. So notice that there's 4 possible inputs. So there's going to be 4 output wires where only one of them is activated. So that's a decoder. All right. The mux, you have A and B. If the selection is 0, you select whatever A is. If it's 1, you select whatever B is. So this has 3. This one, which is a 2-to-1 1-wire mux, has 3 inputs, namely the 2 input wires, a selection wire, and then an output wire of what you selected. Hopefully we're going to do some pictures. Great. Building a decoder. Oh, whoops. All right, here's a decoder. How can we do this? Well, we have these input wires and we're looking for these columns, right? Yes. What's the output column 3? Not 0, but 3, the last one. What is that really?
Oh.
It's an AND. All right, so we just put an AND gate there and we call it a day. Good. All right, so you see what we did there? Out 3 is just an AND. We hooked A0, A1 up to an AND, put it to out 3. Great. How about out 2? No, it's just going to give you the answer. Out 2 would be an AND gate if A sub 0 was inverted. So we invert A0. Notice that the dot or the circle is before the AND, then send it to an AND, and now it's out 2. Okay. Now see if you're paying attention. What would out 1 be?
1 would be an AND gate if A1 was inverted.
All right.
There's a complete explanation.
Huh? Yeah. So then what would A sub 0 be?
That'd be if both of them are inverted.
Right. Okay. Which one of these do you think takes the longest for the circuit to complete? This is a trick question.
They all take the same amount of time.
They're parallel.
No. The AND at the bottom doesn't have anything that needs to be negated first. Therefore, it would be the shortest. Because it's just the cost of an AND.
But it'd just be like all the other three, that would take.
Yeah, so it's very important to understand that these
Really
top
long.
three right here all take the same amount of time to complete. Even though the first one is using 2 knots, they're in parallel, so that takes the same amount as just doing 1 knot. They're both being fed into the and, which I'll say for the sake of argument takes 2 ticks. So if the inversion takes 1, the and takes, we'll say 2, sorry. The total cycle or tick count, or saturation time, I should say, is 3 ticks for this circuit. Why? Because each one of these sections are being done in parallel. So even though, do you see how that's different than coding? So all 3 of these are done in parallel, so the circuit will complete each one of them, or do each one of them in parallel at the same time. Okay, any questions on this?
I have to review this. I only have the question later, but I have to review the first part of the
Okay.
class.
How about a mux? So, let's do the first part. Oh, it just tells you. Great.
Oh, whoa.
The idea is that the output is whatever we selected. All right, so this might be a little confusing. So if the selection is on and B is on, then you want to send that over to C. Correct? Otherwise, if the selection is not on, which the not of it would turn this guy on, it'd be 1 to 1 A was selected over to C. Does it actually give you the truth table for this? So notice that this guy down here is 0 if S is 0, because S of 0, 0 and whatever is always 0, right? On the other hand, this guy's always whatever the value B is, because if this is 1, then it's just going to take whatever is on this side. Same thing's going to happen up here, except only if the selection is the other way, because we inverted it going in. Okay? So, if it's A up here, down here it would be 0. So in order to basically merge those 2 wires and only select one of them, that's why you have an OR. Yeah, you just have an OR. Which condition would not occur right here, actually? Yeah, if you can guarantee both of them were 0. It could happen actually if A was 0 and you selected A, but they both can't be forced to 0. So it's A if S is 0 and B if S is 1. Does everyone see this? What's the total cost or saturation time for this circuit? You don't have to give me an exact number. You can just tell me it's the saturation of this, this, and that.
Be the saturation of B naught with the S, and then
So this not, okay,
the ands take the same amount of time,
So-
and then the or.
and then the OR. So you see that it's just a not, an and an OR in this case. All right. It's called a 2 to 1 mux since it has 2 inputs, 1 outputs. How would you build a 4 to 1 mux?
I'm pretty sure that's not the right answer, Keith.
No. How could we build a 4 to 1 mux? We have a 2 to 1 mux. How can we build a 4 to 1 mux?
I know we need 4 inputs and 1 output.
Right.
I don't know if that's.
More wires.
2 more, good. Well, hold on. You have 2 more wires up here, but you also need another selection wire.
Yeah.
So 3 more wires.
And then you
Two of
need
those muxes and
another.
And then what?
both of 2 of those muxes and another or an and.
Right. We already have a 2x1 mux. No need to recreate that. Just have all those AND wires up here in selection and then hook them up to the mux and move on. Okay. How are we doing on time? All right, we are going to stop here because next time I'm going to kind of review a little because I skipped over a couple things. That's okay because I got you at least started on Verilog. So you can have a lot of time to go ahead and work on your Verilog program.
More than an hour.
I know, more than an hour, so you should actually be able to knock this out. Isn't
If my
that
laptop doesn't die.
if you're lucky?
I have 3%.
Yes.
Bash has not been enabled on here. I need a username.
Okay. Yeah, I'll be right over there.
Oh man, it won't even start now.
It's beautiful.
It's
Any other
good.
questions? Great. All right. Have a good